Okay, Club. Welcome to the 5th class of the summer pre-course, Interactive Mathematics with Mathematica. Let me draw your attention to the syllabus here. Well, this is actually the sort of like item list. In terms of schedule-wise, I think we are slightly behind relative to this, but we will be able to cover. I'm pretty confident we will be able to cover all the materials. So we're sort of like around here, where I left off with transcendental numbers and infinite series and sequence. And today we'll go into vectors and matrices, and maybe matrix operations, and a little bit into, hopefully, we'll get the beginning of matrix representation of system of linear equations by the time we finish today. Okay, so let's go to our Mathematica notebook. By the way, it's actually version 12.3 now, but for this class, you won't need to update. Okay, well, of all the items, that's going to be taught in this class, I could perhaps surmise that some of what I'm going to be describing in the next few minutes would be one of those things where, push come to shove, we can actually skip, because chance of you encountering them in raw form is quite slim. But it is good to know for one reason, the fact that it gets you to the idea that mathematics is not a computing engine in the sense that you put in something, you put in X, you do something to it, and immediately you get some kind of result. That is a very nice way of thinking of the operation, like so kind of one step type of thing. You get you put in X, you multiply by 3, you add 5, and you get Y, and that's the end of that. Well, a lot of time, the results are not achieved immediately. It's achieved algorithmically, meaning that you have some kind of internal computation loops that has to do a few things a few times before you get to the result, which is good enough. Okay, so you don't get the result right away. You have to do some iteration. Okay, you have to add, subtract, multiply, whatever, and then check some condition, and do add, subtract, multiply, and check condition. You have to do this algorithmically, okay? And that's going to be the bulk of computational engine that you will use in your lifetime, okay? So it's not a fixed function, like a sine function or an exponential function or something that you can just put in and get the result right away. Its chances are it's going to be algorithmic kind of computation. Now, first of all, you can't do algorithmic computation without computer. Okay, you could do it by hand, but you run out of paper very soon. Okay, in fact, historically, there were people who had to do algorithmic computation by hand. They were actually known as human computers. And I think there's some Hollywood movie about a black lady in the 50s who actually was a human computer for NASA. I don't remember what the name of that movie is. I think it came up a year or two ago. Okay, that's a true story. Anyway, so back then you had real human computers that performed calculation steps, iterative steps. But now, of course, you have computers. And because computers are so powerful, chances are a lot of application that you would deal with in real life, whether it's machine vision, object recognition, recommended engine, sort of like chatbot or some kind of e-commerce, all this requires something that's not calculated as a single mathematical function, but it's sort of like a process, like I said, an algorithm, like a recipe for calculation. Well, if you go back a few hundred years, before computer, of course, before computers, but a few hundred years, there were also some results that could not be achieved in one step. Okay, you have to do something several times to get some kind of result. But of course, I'm being a little bit facetious because by a few times, it actually meant infinite number of times. And that's what we're talking about in terms of series and sequences. So there were mathematicians, a few hundred years ago, who were working on things that did not finish. Okay, things that you can start but not end. Okay, so let's start with that. So the first thing is called a sequence. Okay, now you might know something like, what's a sequence? Well, a sequence is a series of numbers, okay, but it has a logical way of continuing. So it's not a random, any number you can think of, but it's a number that once you get to 500 number, you want to add the 501, okay, and another number, and another number, and another number, but there's a definite rule to it. And the most famous, I would imagine, for your class is maybe Fibonacci. Okay, let me search a little bit. Fibonacci. Fibonacci sequence. Okay, so now this video, I'm not gonna turn it on right now, but if you type in Fibonacci, okay, so I'm not going to play the videos. You can see them by yourself. If you go to YouTube, you'll see a lot of things like picture of spiral, because the way the geometry works like this. Okay, you can see that the spiral picture. So let's show a picture of a Fibonacci geometry. Okay, you see something like this picture. Yeah, this is a good picture. Now, of course, let me just in case some of you haven't heard of Fibonacci sequence, it's a sequence that start with the number 1. So it's a sequence of number, right? But you start with number 1, and then start with another number 1, and then the next number is generated by adding the 2 previous numbers. So 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, 5 plus 3 is equal to 8, 8 plus 5 is 13, and so forth. Again, this is the first, well, I don't know if it was the first time. It was one of the earliest sequence that fascinated early scientists and mathematicians. Okay, the reason that it's so prominent is because the way it's constructed, it resembles a geometric problem of adding. Okay, so you can sort of like add 2 sides and get the 3rd side, and add the latter 2 sides to get to the 3rd side, and this corresponds to the way nature progressively builds bigger and bigger structure. That's why if you go down to the geometry of a shell, okay, you would see that the ratio between subsequent section and so forth, okay, is determined by this pairwise addition of the last 2 terms, and it gets bigger and it gets bigger and it gets bigger in that ratio. So okay, this is a good picture I want to show. Okay, so you can see that 3 plus 5 is equal to 8, 5 plus 8 is equal to 13. You add the height here, 8 plus 13, you get 21. You add the height 13 and 21 here, you get 34. So if you keep building a rectangle so that the shorter side Okay, the shorter side here, the longer side is equal to the previous two sides, 13 and 21. Okay, you make 34, and you get 21 and 34, you get 55. You can keep creating this bigger and bigger, and the ratio of how it goes up, sometimes called golden ratio and so forth. Okay, so that's why this number is not, this sequence is not arbitrary. Okay, this Fibonacci sequence is not just mathematically beautiful, it's actually the way nature builds or scales. Okay, this is a natural way of scaling in nature. Okay, so nature doesn't scale 1, 2, 3, 4 necessarily. That's called linear scale. Nature scales like 3, 5, 8, 13, 21, 34, 55, and so forth. So this is how nature scales. Okay, and this is from a shell, a cross section of a seashell. And they say that perhaps it's also hidden in the pattern of something even as remarkable as a hurricane. Okay, so you can imagine that this is how the size of the hurricane scales. Okay, so there's some geometric, there's some mathematical, there's some natural sense in which the number progresses. So that's called a sequence. So let's get back to our concept of sequence. Now, in our case, in this case, you know, this thing will just blow up and just keep going infinity to infinity. Now, in your lifetime, you will see a lot of this similar thing. Okay, so whereas you say something like 1 plus 1 is equal to 2, okay, and then 1 plus 2 is equal to 4. Oh, sorry, 1 is equal to 3, and so forth. Like a Fibonacci. What you would have is some kind of system, okay, and you have some kind of input, okay, and then you have output is equal to some kind of system times input, okay, and then some kind of environment state, something like that. Okay, something like this, and then this output then becomes an input. Okay, so this is input 0, environment state 0. So this is output 1, okay, is equal to input 1, okay, and you add this, you introduce environment state 1, okay, and you keep going and you get output 1, okay, and then this becomes, oh sorry, 2, and this becomes input 2, and you keep going. So this is the kind of algorithmic things that you will be doing in real life. Okay, some of it is literally what you do. In other words, if you're going to do some kind of machine learning, you literally do a lot of loops like this. Okay, on the other hand, if you're doing prototyping, okay, you can imagine that this is your idea, this is your prototyping, this is your comment from your client, you get something. You get something, you take comment from your clients, and you get another output. So that's a second version. That's your second prototype. You take that prototype to your client, you add prototype client's comment, and you come back with a third prototype or something like that. There's a lot of iterative processes. So even though in raw form, you would not probably be using a numerical sequence, you know, in raw form, like Fibonacci or something like this. The concept is something that should stay with you, something that is very much part of modern thinking. Okay, it's very much part of modern thinking. So this is actually something of a revelation. The idea that mathematics is not something that you give an x, you do something, you get a function, you get a y, but you actually give an x and you start cranking this machine that outputs something, and then you feed it back again, you crank it one more time, you feed it back again, crank it one more time, algorithmically, until you get to the desired result. Okay, so our design mathematics is a little bit like craftsmanship, you know, like when you are trying to polishing something and you're creating an art craft, you know, you go through a process of refinement. Okay, metalsmith, when they make sword, you know, they beat on the chunk of metal until it gets slender, until it gets to a shape resembling a blade, and then it gets something that's curved, and it finally becomes a samurai sword. Okay, that sort of thing. So human beings are used to iterative process, but mathematics are not used to iterative process. This kind of sequence of keep doing things mathematically forever, or something like that, or up to a certain point. It was something that, in a way, was an innovation, the groundbreaking innovation. So this concept is still with us. Okay. Once again, you're not going to work with sequence in raw form, but in your life, in your career, you would do a lot of things that has this kind of repeated step of computation. Well, like I said, you do a lot of this until you get to the desired result, right? So if you think of a series, the desired result is sort of like the last one. But if you imagine that the desired result is actually the sum of all this. In other words, you don't care about 1, 2, 3, 5, 8. Okay? But you actually care about taking the summation, running summation, so 2, right? Okay, so 1 plus 1 is 2, 2 plus 2 above is 4, 4 plus 3 above now is 7, okay? 7 above is 12 and 20. So you kind of like cumulative sum. So you take the sum up to here, 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 sum up to here. And you do it infinite time, that's what you want. Now, obviously, something like this is going to get bigger and bigger, right? I mean, the term itself gets bigger. So why would the sum get smaller? Well, the sum is going to get even bigger, even faster. But imagine you have something like this. 1, okay, 1 divided by 1, 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 5, 1 divided by 8. You add the subsequent terms are getting smaller and smaller. So your finished product is an addition of all these terms. It's not going to blow up because you're actually adding infinite term, but each term gets smaller and smaller until you basically adding 0. You're adding nothing. Okay, so that's like I said, when you do polishing or something, right? First you polish, you know, you make coarse sand grinding, and then you get finer and finer polishing until you get the final product. Well, that's what the final product of a series is. It's this kind of thing. But what it produces is something that is, well, it is remarkable mathematically. Okay, it's something that would surprise you if you do. If you go back to what was it? Let's go to the YouTube. What was it before YouTube? Infinite series. Okay. You also get a lot of, well, actually, this is the name of the channel, sorry, which I also subscribe to. Okay. But there's a lot of things. It's quite amazing. Okay, it's quite amazing. But I'm just going to show you a few things. So this is the idea of having a series and a sequence. Sorry, a sequence. A series in this case is the sum of incremental addition. Okay, so you add, keep adding, keep cumulatively adding the term in the sequence until you get the finer and finer point. Now, when I say you add, you can certainly add negative term, right? Right? So think about this. Think about this. I want to, well, selling is a little bit tricky example because you actually don't get where you go. Well, yeah, maybe it's not a bad idea. In sailing, you can't go upwind. You have to go left and right, left and right. It's called tacking. Okay. Maybe I can show a picture of the sail. It's actually my father. So my father is going this way, but actually his ultimate aim is this way. So at some point he goes this way, he has to turn left. Okay. And then at some point he has to turn right. So if his objective is here, he's heading here, 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 here. Okay. You can imagine that you do that and you get something that you want. And this exactly is a lot the way some of these series work. This, and this is a little bit hard to explain. Okay. Now, what does this look like? What does this look like? I actually put this down here as the final result. So if I keep adding this term, now let's do this. Let's do this. Okay. So what's the first term? I is equal to 1. By the way, I hope you're familiar with notation of summation, right? So this is a good place as any to start the notion of summation. When I is equal to 1, you put I is equal to 1. 1 times 2 is 2. 2 minus 1 is 1. Minus 1 to the power 1 is minus 1. So that's the first term, right? So you add this. So this is saying that you're doing this. You're doing this. You're doing this. Okay. Now, if I want to add the second term, I just add to the second term. So now I do this. Okay, let's see what I get. I get minus 2 over 3. Okay, so let's say I add 4 terms. That's like something like this. 3, oops, 3, 3, 4 terms. Okay, right? Now watch this. Watch this. Well, let me just show you with manipulate. It's easier. I going 1 to say 10. Okay. Step up 1. And so it's going to go from minus 1 to 1/3 to minus 1/5. Okay. So it's going to go back and forth between positive and negative. Okay. Positive and negative. Let's start again. Okay. But the term gets smaller, right? So basically you get something like this. You get something like this. So you get something like minus 1 plus 1/3, minus 1 plus 1/3, minus 1/5, plus 7, minus 9, plus 11, minus 13. So you can, it's like my dad sailing, right? So before he gets to the target, he might have to make a big move. Okay, but once he gets very closer, maybe a small adjustment. Okay, that sort of thing. That's an analogy. Well, it turns out that if you do this big enough time, okay, if you do this big enough times, oh, let's me, okay, if you do this big enough times, okay, you get something that's close to this. Now, this number, for some reason, okay, well, it's not for some reason, for well-defined reason, if you multiply this minus 4, okay, put this in the bracket, sorry. Okay, minus 4. It starts to look at like number that you kind of might remember. Let's try again. Let's start with 10. Okay, it's 3.04. You may not recognize it. How about 100? 3.13, and that's sort of hinting at where it's going. 3.14. Anybody remember this is? This is actually something that approaches the value of pi. Okay, so Mathematica knows this. So if I put in this here infinity, it's actually going to give you pi. Okay, it's going to give you pi. Now, another way of saying this is to say this is the number of iteration, and let me use the notation of the limit. Where's the limit notation? Limit. Okay, limit of this of n as n's go to infinity. This is actually the expression. So you are adding the first 10 term, 20 term, 30 term, 100 term, 1,000 term. You cannot stop. You can keep going. Okay. But the point is that once you get to say 1,000 term, okay, like a human computer can only do 1,000 term, you already get pi to a very good approximation. Okay, you already get a very good approximation. Now, this thing happens to know that once you get to pi to infinity, you get pi. But if you get something like this, then it's not very, you know, if you get something like this, 100, then it's not quite close. Okay, it's 3.13. That's not good enough, right? That's not good enough. So the human computer, if you do the 100 term, it's not good enough approximation for NASA, say. Okay, so for NASA to launch something in the orbit, and you need a human computer to do it, you need them to do it, put in, you know, over time in order to get to this level of precision. And of course, you can keep going and you get higher and higher precision. Okay, so you get something like this minus pi. Let's see how big it is. What's the difference? Well, anyway, you get some closer approximation. So anyway, that's it. That's all I want to say about the notion of sequence and series. So you have that, okay? And in the notebook, you have a lot more things, okay? For example, this one here, okay? This is a difference. So this is the right-hand side. I know that it's going to approach this because mathematics tells me this is going to approach this. So what I'm going to do is just to plot this as a number of approximation term increase, okay? So for one term, the difference is a lot. For two term, it's still big. So by the time you get to 50 term, the difference is very tiny. And this is how you actually had to do a lot of computation before you actually had computers. Okay, so that's it. That brings us to this. Okay, now final thing I want to mention is that infinite series like this is how people could arrive at number of what's called transcendental numbers. Now, transcendental number is number that came with the universe. Okay, it's number that came with the universe. Human being cannot make it. Okay, human being cannot make it. What can human being do? Human can make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? We can make this number. Integer. We can make integer number. We can divide them. And we get rational number. In other words, if we get something like big integer divided by another big integer, okay, and let's see what number that comes up to. For some reason, this is not executed. Oh, that's kind of weird. something wrong. Okay, maybe I put something symbolic in there so it doesn't know. Anyway, well, 2 divided by 3 is. Oh, sorry. The reason it's not doing it is because I sent it to execute something and it just hasn't come back. Yeah, let me just make life easier and just start over. Sorry, I accidentally set it to a computation, so it didn't. Right. So, like I said, what can human being do? We can make big number. Okay. We can make another big number. Okay, and we can divide them. Okay, and we get some number. Okay, this we can create. Human being can create this number. Okay, so if you can count on your hand that many times, you can count on your hand this many times, you can divide, you get something. This is called rational number. It can be expressed as ratio of 2 integers. It may be a funny integer, but you get this. Okay. What human being cannot do is something like this to create pi. So things like transcendental number. Okay. Transcendental numbers. These are numbers that cannot be expressed as ratio of integers. Okay. Well, those numbers cannot be calculated using anything but this kind of formula, this kind of infinite series. Okay. Log of 2 is one, I think it's one of them. Pi certainly is. E that we encountered last time. Okay. So that's it. So that tells you that even before computers, people were trying to do things algorithmically to get at some result. Okay, that cannot be achieved in one shot. You cannot create pi in one shot. You can only successively get closer and closer and closer to the value of pi using that infinite summation of sequence. In other words, series. Okay, series. Now, later on, you will run into this thing called time series. Okay, so let me prevent your misunderstanding by just writing it out here. Series, okay, yeah. Series is a summation of sequence. In particular, most series I was talking about is infinite series is a summation of infinitely long sequence. Yeah. Infinitely long sequence. Now, time series, okay, despite the name, is actually not a series, it's a sequence indexed by time. It's a sequence. It's not a series. It's a sequence. But having said that, they're not completely wrong to say that this is a time series. Why? Because instead of, okay, let's think of something. Let's say time series, financial time series. Okay. Stock price, okay, is a sequence of stock price in time, indexed by time. In other words, you have price of stock today, yesterday, 5 months ago. That's a sequence of stock price. But the reason it's allowed to be called series is because the way it's constructed. Because you can think of as price, okay, on day 1, on day 1, okay, as something, okay, and then price of day 2 is equal to price of day 1, which is x1, plus price change. Okay, so if you think of day 1, price of day 1 as the first price change, even though it's not a price change, it's actually initial price. If you quote unquote allow it to be considered a price change, okay, from 0, price change from 0, okay, and you add price day 2 is this, then price of day 3 is equal to price of day 2 plus price change, okay, on that day. Okay, so you keep adding, okay. So you can say that in a way, time series is a proper series because it keeps adding the changes, okay. So you see that. So for all intents and purpose, when you see time series, each value is actually a sequence, but it's called a series because internally you can think of it as being created by cumulative sum of changes. Okay, so that's why it's called time series, not time sequence. So I think that's a good reason why. So you see a lot of that. Okay, so if you go into financial, whether or not you're dealing with real currency, Thai baht, dollar, sterling, or you go into cryptocurrency, it's going to have this kind of dynamic. Okay, price of Bitcoin is a time series because it has a value for every single day. In fact, it has value for every minute. Okay, but we can say every day. So it's a time series. So you'll be working with that. Okay, so again, even though you will not, I repeat, you will not be working with a lot of this series and sequence in raw form. The thinking behind it is something you're going to be applying. Okay, the idea that you don't get something in one shot, but you get sequence of it. The idea that if you want to get a final product, you keep adding refinement to it, okay, until you get the final product. That's the series thing. Okay, this is something that will be part of your critical, logical, and analytical thinking. And it's also part of business model. Okay, let me just make one final sidetrack. In the old days, when you do project, whether or not it's IT project or product launch or something like that, you do things in one chunk. You make the requirement and you tell the requirement to the engineers or the IT, and they give you that thing at the end of the day. It's like a promise. Okay, it's like buying a car with a spec, a proper spec. So you commission somebody to build you a project, and you go away for 6 months, and you come back and you get the result. Okay, but that's in modern terminology, it's called waterfall. It's like a big chunk of thing coming all at once. But now you don't do things that way. You do it incrementally. You start with a prototype project, and a week later you refine it, and a week later you refine it. It's doing things in a way, the same way that mathematicians 300 years ago were producing pi. You can think of it that way, okay? So mathematicians 300 years ago were producing pi, doing this thing sequentially. Well, now, when you do a project, like a product launch or app development, you're doing it sequentially as well, right? And you keep refining, keep adding tiny amount to it, okay? It's not a big overhaul, and that's called agile project management. And so in your buy-side education, you are going to be doing a lot of project-based learning. And by project-based learning, it is going to mean agile project. It's not going to be a waterfall project. Okay, maybe for some historical reason, our faculty will probably teach you a little bit about waterfall project management. But most of the time, I think in the future anyway, you should
be introduced to agile project management. And so your project learning, your project-based learning, or your actual project, whether or not maybe your senior project or whatever, your actual project is going to have this kind of thing, you know. So you overshoot something, you undershoot something, overshoot, undershoot, and through successive sequence of iteration, you get something that is near optimal. So that's that. Okay, so let me finish and go on to linear algebra. And this is where, to be honest, this is where you start to work with Wednesday's schedule. Now, okay, let's go to Mathematica. Okay, so you have seen that I can create a set of things, right? Set of things, set of numbers. Okay. Now, technically, if this were a set of number, okay, I can switch the order around. If this were really a set of number, okay, if this were a set of number, I can switch the order around, right? Because whether or not I have meat and potato, or I have potato and meat on my plate, it's the same thing. So whether or not I have 1, 3, 5, and 7 on my plate, or 1, 5, 3, and 7 on my plate, it should be the same thing. What this is not just a set of numbers. It is actually a list, an ordered list. So that when you do this, it's false. Okay? It's false. It's not the same. It's not the same. Now you can add something else, whether or not it has the same number of elements and so forth. You can check. There's some set operation that you can do. Okay, but that's not the point right now. The point right now is that I am going to use this construct, and this construct, by the way, is called, well, first of all, what is it? It is an ordered list of numbers. It's an ordered list of numbers. Okay, it's an ordered list of numbers. I put in a bracket where the number of numbers, meaning how many numbers there are, or length of list, is fixed. Okay, so this is what I'm going to talk about. I'm going to talk about an ordered list of numbers, like 1, 3, 5, 7, 2, 2, 4, 2. Okay, this is an ordered list of numbers. Now, if I did this, I have to make sure I specify the number of numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there must be 10. So every time I'm talking about this thing, I must have 10. Okay, I can't talk about this and then go on and talk about this as if they are, you know, similar kind of thing. It's not. Okay, it has the same structure, but it's not. Different kind of animals. Think of it as your genetic code, right? Your genetic code, your genome, is certainly not the same thing as a mollusk. Okay? It may be longer. Human genome may be longer. Some animals, some simple animals have longer genome sequence than human beings. I don't remember what they are, but you can find a lot of them. Anyway, so it's not compatible. Your genome and a mollusk genome or a platypus genomes are not compatible. For one thing, well, they're not compatible for many reasons. But first of all, they don't have the same length of gene. So it's very important. This thing is called a vector. Vector. This thing, or the list of number where the number of length is fixed, and the length of the list is called dimension. Okay, length of list of dimension. Now, this is just one vector. Now, let's say I do this, and all I did was just switch the order around. it's no longer the same individual. It's like just because you have two human beings, they have the same length of genome, but the genes are not different, are not the same. Okay, by swapping one gene, you are a different human being, different animal, or a different person. Okay, so this thing is not the same thing as this, but they have the same number of dimensions. Okay, so how do I represent this? I'm going to represent it with a variable. Now, remember we did this before. X is a variable, is equal to 5. Would that just represent some kind of number, right? Well, in this case, I'm going to say X is representing a vector. So mathematically, if you're talking about something that has one value, you say X element of it's a real number. Well, anyway, I forgot the special character for real numbers, so let's just go to here. Okay. So if I did this, okay, X is an element of real number. In other words, it's from minus infinity where's the infinity sign? Okay, to plus infinity. Okay, so for example, if you say this, you can say something like X is equal to 5.321, or you can say X is equal to pi. Okay, you can do that. Select that. Okay. Now, so that's just one number. How do I? It's a bit clumsy, so let me just work with 4. Make it a little bit easier. Okay. How do I deal with 4? Okay. Well, to deal with 4, it is to say something like this. So now it's no longer this. It's a list of number, each of them being a real number. So to write it properly, X is equal to X1, X2, X3, X4. Okay, where X1 belongs to this, and the individual, all of them, belongs to this. Okay. Now let's have that fixed in your mind. Okay. I declare that X is a variable, but I am going to define it as a vector of dimension 1, 2, 3, 4. So it contains 4 numbers. It's a list of numbers, and I can't do this. This will make it wrong. I can't do this. So if it's an ordered number, okay, so it has to have the right place, X1, X2, X3, X4, where each of them is a real number, and there are 4 of them. So this is n is equal to 4. So n dimension n is equal to 4. Okay, so that's the vector. Now, let me do this. If I were to write this for 100 of them, it would be a little bit too clumsy. So what I'm going to do is X is equal to array. Okay, we use the word array, so we'll call it value. So to distinguish the value from this, so I might say something like X vector to emphasize, it's a value of x from dimension 10, I think. Can I do that? Yeah. Okay. So dimension 4. So right away, it's assigning x 1, 2, 3, 4. Okay, but it's using this notation. It's not writing like this. It's not writing like this. It's using notation. If you think about it, you can think of the index as an input. So, for example, if I did this, and I say x vector, okay, and I put in the fourth element. So I put in fourth element, okay. Now, in this case, the notation you have to put in bracket twice, okay. And it will turn into this kind of like emphasize bracket. Like you're looking for the element. If you did this, it's going to give you. Oops, sorry. The fourth one. Okay, so it's like it looks almost like a function. That's why I use this kind of funny notation. Okay, it looks almost like a function, but it's giving you the fourth element. Okay, so let me do that again. So let's say if x is a vector like this, now let's say y vector is equal. Now I'm going to give it the real number. 3, 4, 1, 7. Okay. And I do the same thing here. It's going to give you, okay, x4, right? It's just an array, right, of x, the fourth one, no value to it, but y has a value. So the first one, the second one, the third one, the fourth one is 7. Okay. So let's go to the third one. Okay. The third one is 4. Yeah. The third one happens to be -4. Right. So this is how you refer to each element of a vector. Okay. Now, in a textbook, this does not look nice. Remember, this looks like a set. In a textbook, if you see something like this, it's a set. But this is how you put in the vector in mathematics. So to make sure that you can say write scientific paper or write the right notation, you can pass this to a function called matrix form. Matrix form of y vector is going to give you that thing that you see in the textbook. Okay. Okay. So it's give you this thing. So sometime you would see the definition of vector is defined as column of number. You see that a lot. Okay? But technically, it's just that the reason you write it in a column is a convention. It's a convention. Yeah, it's a convention. Okay. So that when you see this in the textbook, you say, oh, that's a vector. In fact, that's an ordered list of number of dimension 4. Whereas if you see something like this in a math book, it's just a list of items. Okay. So again, this is list of items in a textbook, but in programming, in Python, in Mathematica, this is how you would write a vector. Now, Python, I think, Python, we use different brackets, right? I think we use
for the list, right?
in Python, I think if you want to say vector x is equal to, you have to say something like what square bracket first?
Actually, to build the vector, we need use the numpy array.
Forget numpy array. Just normal array. What would it be? Bracket, right?
Yes, square bracket.
Okay, and then separate by one. Okay, something like this, right?
Yes.
Yes.
And how do you access individual element?
Yeah, also use the square bracket.
Square bracket, but just one square, right?
Yes.
Yes.
Okay, gotcha. Something like that. Okay. So again, I can't use a square for this, but we use this. So now we have a vector. We have like a list of column of number. This is the most fundamental object that you will use in your life. I'm not exaggerating, okay? I'm not exaggerating. For example, now, let's just say, okay, let's just say you are selling clothes, all right? You're selling a clothes, right? Some kind of t-shirt or something, okay? And your client, you have to take a measurement. Okay? This is how your client would look like to you. Okay, your client would look like this to you. Okay, client is equal to. Okay, let me write the matrix form. Something like, say, 1.7, 1.69, and 72, and 33 and 36 or whatever. Okay. Okay. This is what your client looks like to you. Okay. Because your client is 1.69 meter tall. Okay, let's make it 1.69. Okay. It happens to be that this has the unit. This is centimeters in height. This is kilogram in weight. And let's say this is waist, I guess, in centimeters or inches? Centimeters, inches. And this is maybe like an inch. Okay. So for every problem you are interested in, you are interested in attributes. Let me say that again. For any problem you are interested in, every object that you are handling, whether it's your client, it is a business project, it is a product, a design parameter of some kind of gift or product. Okay? At the end of the day, they are represented by a vector of number. Okay, so get used to this idea. I'm going to write this really big. So you, okay, vector represent objects in life. Okay, each element of the vector represent the attribute of say object. Yeah. So if I say vector represents your client, and I can say something like second element of the vector then represents the weight of client in kilogram. Okay, and maybe the first element of the vector represents height of client in centimeter. Okay, now you can see why you cannot switch things around, right? Okay, so you can write things in the right column. right? So what happens when you have more than one person? Well, you can have X is equal to client 1. X is client 2. Okay, so how would that look like? Well, it would be a list of number. So you have something like this. So maybe, so this is Bob, this is Alice. Alice is a little bit shorter and weighs a little bit less. So 52 and smaller, but very tall. So maybe as inches, something like that. So this here is one person, 4 attributes. This is another person, 4 attributes. Okay. Now, can I put in a person with 5 attributes? No, it wouldn't work in this set, right? Because you have to define that here we have dimension is equal to 4. Is equal to length of the list is equal to number of attributes. Okay. So how much details you have on your clients is about how many attributes. By the way, you probably have heard of the word big data. Well, big data, right here, I can tell you what big data means. Big means you have a lot of clients. Big also means you don't have just 4 dimensions, you have lots of dimensions. And finally, big means you have very diverse representation. This here can represent the height, but you can have some number that represents some kind of dress, some number that represents some kind of eye color. So it's very, ultimately, it comes down to numbers because, computers only work with numbers, but you can think of it as something like brown hair. Okay, whereas another person would have something like black hair. Okay, so you have something like this, and then you have phone number. So for number of Bob, Alice, Ford. Okay, so with big data, what it means is that you have a lot of items, you have a lot of dimension, and a lot of those dimensions are not intrinsically numerical. They have to be converted. Ultimately, this has to be converted to numbers. But when you start collecting the data, they comes in various forms. It could be a picture. Yeah, and that would be something like big data. Okay. So, but we'll talk a little bit about that in other class, obviously. So now we have the most fundamental thing about this thing called vector. A vector is the most fundamental things in your life. Now let me quickly do something to show you that you have seen this before. Okay. You have seen this before in tabular data, right? So this is person. So this is person, Alice, Bob, okay, height, weight, inseam, say whatever, right? So 158, 169, and 72, 32, okay, 36, 32. Now, you will notice something. It's written in the opposite way, right? So whereas with this example, well, I just erased them all, okay? You would list something like 169, 72, and 32, okay? And so this would be Bob, and this is Alice. You would list it this way. So this is a vector. This is a vector, right? This is a vector. In Excel, in table form, you normally don't do it that way. The reason is that the dimension is usually small, but the number of times is usually 1,000. So if you did this, you would have to write many columns. And as you know, Excel has a lot more rows than it has columns. So the designer of Excel, to put attributes that would be ultimately vectors, they flipped it. They make this into a vector that lies sideways. Sometimes to specify this is called vector. It's also called column vector. And this is called row vector. Okay? So you can think of tabular data in Excel as a list of row vectors. Okay? So you can have like maybe 50 dimensions here. That's a lot. But certainly you can have 2 million customers here. Okay? You can have, in Excel, you can have how many? Oh, you can have 1 million and a bit. Okay, that's a limitation in Excel. So with Excel, you can only have 1 million customers. Okay, but with Mathematica, with Python, you can have more than millions. Okay, customers, and so forth. So there it is. So this is just to relate to what to read. So when the computer reads this, you have to bear in mind that it's kind of lying sideways. Okay, so now we have the notion of vector. Now we have the notion of vector. Let me introduce you to another notion of vector. Okay, this first notion is the notion that it is a notion that, let me write it again. Vector represent object, and n-dimensional vector represent object of whom you have n attribute information. Okay, now, so write this in your head, in your mind. Okay, vector represents object. Vectors represent object. N-dimensional vectors represent objects, okay, of whom you have information on n attributes. Okay, human beings have many dimensions, but if you are selling the person t-shirt and jeans, you don't need to know the distance between the left eye and the right eye. Conversely, if you are selling glasses, you're doing prescription glasses, you need to know the distance between the left eye and right eye of the clients, but you don't know the inseam of that person. Okay, so it depends on what your problem is, the information, the attributes that are relevant. Okay? And that depends on your problem. So that's the first notion of vector. The other notion is vector represent coordinate. Okay, now this is a little bit limited. It's a little bit limited actually. Why? Because how many coordinates can you have? Well, actually in life you only have 3-dimensional at most, right? You can plot that. So let's okay, let's think of now. So you can think of okay, let's do this. Let's go. I don't know how to do this. I want to draw, okay, free form input draw arrow from origin to 1, 1. I don't know if it works, okay? Let's see what mathematics goes. Okay, so this is like using the free form. It's asking Mathematica to think. Oh, no interpreter. Draw arrows. Okay. How about draw line from 0, 0 to x and y. That's what. Okay. Oops. Coming with anything? It's getting anything? Draw a line. No interpretation. Oh, okay. It gave something. Hold on, where it go? Where did it go? It went somewhere. Okay, there it is. Origin where something begins. So it doesn't know what you mean by origin. Okay. So anyway, so I'm just gonna say what you need to do. So for example, plot. Okay, plot F1. So if I want to plot a line, okay, I can actually do this. List plot from 0 and 0 to 1 and 1. Okay. Oh, sorry. Okay, so there. Okay. Now, forget if I don't make a join through. Let's take that for a minute. This is what I mean by a vector is a coordinate. Now let's work in this case for 2 dimension. Okay, 2 dimension. What is this? This is a vector of 2 dimension. This is the value of the x coordinate or horizontal coordinate. This is the value of the vertical coordinate. So in this case, 2-dimensional into D. Okay, so that's why the number or the length of vector is called the dimension to begin with. Why don't they call it length of vector? They could, okay, but they call it dimension in anticipation of the fact that a vector can be used as a coordinate. So if you go from here to here, you go from 0, 0 to 1, 1. Okay, and so this is one vector. Okay, now normally, let me just do this. This is just one item. The vector is actually a coordinate 1, 1. I give you another vector. Okay, so it's 1, 1, 3, 4. These are 2 different vectors. It's a coordinate because it tells you the location. Where are you at? On the x-axis, on the horizontal axis, I go to 1 unit. Okay, actually this is 1. It just kind of does a funny scale. Let me. So let's do this. Okay, let's do it. So it gives you 1 at 0, 0. It gives you 1 at 1, 2, 2, and 2. That's this guy. And 3 and 2. So that gives you a coordinate. Okay, that's the coordinate. Now, what can you do with a vector? Okay, what can you do with a vector? Okay, let me start with this vector, right? Let me start with this vector. Okay, this guy. This is where you are, right? This is where you are. Let's say I want to go twice as far. Okay, go twice as far. Where should I be? I should be here, right? 4 and 4. Well, that's exactly what multiplication does, right? Simple as that. 2 times this is equal to 4 and 4. Okay? What if I want to go the other way around? I want to go to -2. Go to -4 and 4. I can go back and forth all day. I can go back and forth all day. Okay? Now, I'm going to introduce something that's very interesting. Okay? What if, and I'm going to motivate it with the real problem. Okay? Let's just say that, I might as well give you this. Let's say x is equal to 0.4 and 0.6. Yeah? 0.6. Okay. Now I'm going to show you what it looks like, right? Matrix form. Yeah, it looks like this, right? So x. Now I'm going to use a different word. I'm going to say that this is investment. How much money do you have? Let's say you have 4,000 baht here, and you have 6,000 baht here. So you have 10,000 baht. You have 10,000 baht. You separate it to 2 piles. Okay, one pile has 4,000, the other pile has 6,000. Okay, now you invest this one. Let's say return is equal to, let's say you invest this one in stock. Okay, and for this period, your stock loss minus 0.01. In other words, it loses 1%. But you put this 6,000 baht into a fixed interest, and that fixed interest is positive, but very small. So you get something like 2%. Yeah, 2%. Now, obviously, your gain loss is equal to what? What's the gain loss? It's equal to this times this plus this times that, right? So let me do that. Okay. So basically, it's this times this plus this times that. In mathematics, this kind of element by element multiplication. Okay, so you have to line them up, multiply them, and add the sum. It's called a dot product. So how much money do you make? Investment dot return. Okay, is 80. Why do you make 80 baht? Because you gain 2% from this. What's 2% from this? It's 120, right? 2% of 6,000 baht is 120. Okay, what's 1% loss on 4,000 baht? It's 40 baht. So 120 baht minus 40 is 80. Now, the convention, okay, I should use a drawing. The convention here is the way it's written in mathematics. Okay, let me draw this. You write, oops, let's make it very thick. I'm going to make it thick. Okay. Okay, let's say this is my investment x1, x2. Okay, this is my invest. So in math class, you see something like this. This is vector. Now, your return is also a vector, R1 and R2. Okay, but in order to multiply, you have to turn this sideways, R1 and R2. Okay, you take this guy, you multiply by this guy. You take this guy, you multiply by this guy, and then you add, and you get the result. Okay, now, so that's a little bit, that's what you would see in a math book. Okay, this is called vector or row vector. This now is called column vector. Let me show you how this works in Excel. We can do this in Excel. Okay. Now, again, it's a little bit silly. It sounds a little bit silly. Why do things this way? But I'll show you why later. Okay, so normally this is what you would do, right? So this is my return. Okay, so what is it? Minus 1%, and then plus 2%. Okay, and this is my investment. 40%. Oh, 40. Sorry, 4,000 baht. Okay, and 6,000 baht. Okay. So let's make this a currency. Where's the currency? Okay, so 4,000 baht. Normally, the way you would do is this multiplied by that is this multiplied by that is equal to, okay, gain loss, okay, is equal to sum product of this, comma this, right? That's it, 80 baht. Just like before. Okay. Now, mathematically, and again, sounds like much ado about nothing or or a little bit of a hard work. Let's make things difficult. Let's do this again. Now, I'm going to do this. Paste, but I'm going to come down here. Can you guys see this? Paste special. Okay, transpose. So transpose is the idea of taking the thing that stands and lie it down. Conversely, if it's already laid down, over here, and you transpose, it stands up. Okay, so it's sort of like up and down. Okay. Well, this is what you mean. This is what I want to do by a dot product. This multiplied by this plus this multiplied by this. Here, I would say equal to MMULT. Don't ask me why. Of this guy. Oops. Comma of this guy. So the word dot product is written as MMULT. Okay. So this dot product we did here, right? The same thing as MMULT, but you have to put the one line down on the left hand side, right? So remember this picture for the rest of your life. I mean, you should have a nicer picture than this. So let me search internet for a nicer picture. There's a nice picture of a dot product. There's a nice picture of a dot product. This is not that nice, but it's close enough. Okay. See, this one times this one, plus this one times this one, plus this one times this one is equal to that. Now, the notation here is not that nice because normally you write this thing on the bottom here, sort of like that. It should look a little bit like this, but never mind. Okay. Okay, so you can see that this is a column vector, This is row vector. This is by definition. You have to specify. So how do I specify this? How do I specify that one is standing up, one is lying down? In other words, investment is, okay, what is it? It's a real number, right? Real number of dimension 2. Okay, 2. Now this one, okay, this one, technically, if you put it on the left-hand side, is dimension 1 by 2 or 1 cross 2. So I'm going to say this is my convention now. Instead of just putting the length of the vector, let's just make something interesting. It's saying that 1 and 2 is the what? 1 is equal to number of the what? Rows. Right? Oh, sorry, number of row, number 1 by 2. Sorry, it's 1 by 2 is number of columns. Row, yeah, number of row. And 2 is equal to number of columns. Yeah. Okay. So in this case, this thing 2 is the same thing as 2 by 1, or number of columns by 1 is equal to the number of rows. Okay, but that's a little bit silly, right? It's a little bit silly. So you say that this one, this vector here, this column vector, okay, this column vector has 2 rows and 1 column. And the row vector has 1 row and 2 columns. So it's a little bit silly. You only need number 2. You don't need 1 by 2 or 2 by 1. Well, obviously, there's a reason. Because I'm going to generalize this thing to I can do this, right? So now, instead of talking about this guy, I'm going to talk about this guy. I'm going to talk about this guy. How do I talk about this guy? How do I describe it? It now has 2 rows and 2 columns. It now has 2 rows and 2 columns. And that's what we call a matrix. Oops, sorry. By stacking, okay, multiple columns to the right, one to the right of another, okay, okay, by stacking multiple columns or by stacking n dimension. So right now I'm going to change the word a little bit. I'm going to call m dimension. I'm going to say make dimension vector to the right, one to the right of another, okay, by stacking how many multiple? N multiple. Okay, so now I have a vector. So if I have a vector of dimension 2, I can stack it 3 times. Okay, so okay, so now I have a vector of dimension 2, vector of dimension 2, vector of dimension 2. I stack it to the right 3 times. Now effectively I have how many rows? 2 rows. And how many columns? 3 columns, right? You get a vector. You get so like fusing of these vectors, which I call matrix. Of dimension m by n, where m is number of rows, n is number of columns. Okay. Okay. Now, let's see how we can make one. Let's see how we can make one. Now I'm going to use symbol, okay, just so you get this picture in your head. Let's say my matrix.
อาจารย์ครับ
Yes.
There is a question from the student.
Yep. Go ahead.
That how can I type the dimension over the real number letter?
Type that what? Oh.
The dimension.
Control and this sign, this symbol, this thing. Okay. So if I say something like R control, it's going to give you this, and then okay, that's a shortcut for. It's the same thing as this thing. The same thing as this thing. Okay. So the shortcut is control upper arrow.
Q.
Okay. So now I'm going to talk about let's create one. Okay. Now by convention, by the way, let me say this. In most textbook, okay, if you have a single variable like x is equal to 5 or something, this would be sort of like a small x, but not boldface, a thin character. If you see a vector, they would use a small character but boldface. Okay. If you see a matrix, they would use a capital letter. Okay. So for example, A is an array of value A, okay, of dimension 2 by 3. Okay, now it doesn't look very nice. Okay, so I'm going to write it in a format. Okay, matrix format. See that? How many rows is that? So mathematically, you say something like A is element of, that's a special character again, R, okay, shift upper arrow 2. Now, there's actually a symbol by. It's not multiplication. It looks like multiplication, but it's like a flat. We can just use multiplication for now. Okay. Actually, it is no different because it's in fact 2 by 3. By is also a word for product because after all, how many elements do you have? If you have 2 rows and 3 columns, you have 6, right? But you write it like this. You never write this. You got 6 elements, but you never write 6. Okay? Because you don't know if it's 1 row, 6 column, 6 row, 1 column, 3 row, 2 column, 2 row, 3 columns. Right? So you have to specify the architecture. It is by this. Okay? So it's m by n. So you can write it like m by n. Okay? So keep that in mind. So this is defined as matrix is equal to array of number. See, that's why we use this definition array. Array of number, okay, with m rows and 3 n columns. And to emphasize the fact that it's a rectangle, you see this definition. Matrix is a matrix of dimension m by n. It is defined as rectangular array of numbers with m row and n column. So now you can think of the index as coordinate, but it's a coordinate like east-west. It's coordinate of which element. So if I do this, okay, watch this. This is what I get, right? I want to, let's make it bigger. Okay? Let's say I want this guy. I want this guy. This guy is the second element. You can see that it's a second element. Sorry, second row, 1, 2. So walk down 2 steps. Walk down 2 steps. Walk to the right. How many steps? 1, 2, 3, 4, 5, 6. And you get 2, 6. How do I get that? I get a, get double bracket, okay, double bracket, 2 and 6. Okay. Now it had by design I made it this way, right? Okay. So I'm gonna reassign a. I'm gonna make a is equal to, and I'm gonna create this myself. I want the first row to be A, B, C. The second row to be D, E, F. Okay. So this is the first row. This, if you think of it, you can write, you're writing this. This is what you're writing. Second row. First row, second row. Okay. That's it. You're done. Okay. Again, it doesn't look nice, so let's put it in the right format. Matrix form of A. Now you only do this because you want to typeface. You know, you want to show the picture. Okay, but when you do calculation, you just work with A. You don't work with this. See, A, B, C, D, E, F. Now, let's say I want to get E. How do I get E? How do I get E? I have to walk down 1, 2, and 1, 2. So let me see if I get that. Okay, so A, double bracket, go down 2, and go across 2. Now, what about C? What about C? How do I get C? I go down 1, I go across 3. Okay, see that? Now, I'm going to do some magic. Okay, so this is my matrix, right? This is my matrix A. Now, I'm going to call my vector X. Okay, let's say X. X is a vector, is an array of X of dimension 3. Sorry. Oh, I have to clear X because I kind of made, I made a prior assignment. Okay. So now let's do this. Oh, sorry. X vector. Oh, I haven't cleared. Okay, and now x vector. So in a math class, this would be like thin, not bold face, and this would be like a thick. So we can do this, by the way. In Mathematica, you can use special character for some, and even though it's x, it's actually a different x because it's different font.
ใช่ด้วย45ด้วย
Sorry? Okay. So if you use different font, it's actually different value. So I can go to different x here. Okay. So this is my script x. I can do that. Okay. So let's do this. Okay. So this would be like in the textbook, this would be a thin, this would be a bold face. But okay. So there, that's my array. Now watch this. Watch it. So this is my x. So matrix form A, matrix form X. Okay, let's put them side by side. Okay. Now, you guys notice anything? You guys notice anything? Well, if I block this, if I forget BEF, forget BEF, okay? Just ABC. This looks like what? This looks like a row vector, right? And row vector next to a column vector, it looks like you can do multiplication, right? A times x1 plus b times x2 plus c times x3. Well, you can do this here, except now that you have two rows, you just do it twice and list them. Okay, so let's see what happened. A dot b. Okay, now I'm going to go ahead and write that in matrix form. Yeah, matrix form is a little bit clumsy to write, but you only need that to make a textbook or something. But okay, oops. See that? So let's put them side by side. Okay. By the way, I can make it look nicer by putting it in a grid. Okay, and some kind of frame. This is just formatting. Again, it's always a little bit clumsy to do formatting just to make it look nice. Okay, but this is what happened. I have a matrix A. This is A11, A12, A13, A21, A22, A23. This is my vector X. And I just mentioned to you that ABC looks like a row vector, and this looks like a column vector. Well, it is. And you know that you can do this dot product, this times that times this times that and this and that. And you get A, x1, B, x2, plus C, x3. But now you have the bottom, D, E, F, right? So notice you have A is A is a 2 by 3 matrix. The X is a what? 3 vector, 3-dimensional. Or what's a 3-dimensional vector? It's a 3 by 1 matrix, right? Right? Because it has 3 rows and 1 column. And then A dot B is a 2, get one number, by 1 matrix or vector. Okay. You can see that? You can do this dot product, one row at a time, and you get 2 number. This is addition. So this is all one number here. The top line is one number. The bottom line is another number, right? And in fact, what else can I do? What else can I do? Well, what if I did this? What if I did this? Let's just say I have an XY array. Okay, is equal to, now I'm just going to make this, okay? X1, X2, 1, X2, Y, 2, okay? X3, Y, 3. Yeah, I'm just going to make this up. Yeah, I'm just making stuff. And now I'm going to do this. But now instead of A, I'm going to XY. Yeah, let's call it that. Okay. And oops. See that? Just as you see that it's a stack of row vector, this is also a right-hand standing stack of column vector. So you can say A times x1 plus B times x2 plus C times x3 and put here in the top left. You go down here, you do the dot product, you put in the bottom left. And then you go to the right. So this is kind of like a matching, right? So top left, bottom left, bottom left, top right, bottom right, bottom right. Now guess what is the dimension of this? This is 2 by 3, 2 row, 3 column. This is 3 by 2, 3 row, 2 column. You end up with a 2 by 2. So in general, so we have vector, dot vector. This is a row vector, dot column vector. Okay, we did that. We also did matrix, dot vector, provided what? Provided matrix has same number of row as vector dimension. Okay. Finally, what we have is a matrix A dot matrix B, provided A has same number of column as B has number of row. Okay. So this leads to a generalization. If I have this, okay, A is m by n. Okay, let me do this. A is m by k. Okay, meaning it has m row, k column. You know what's coming next, right? B is k by n. K row, n columns. If you multiply A dot B, okay. By the way, in mathematics book, sometimes you just see this with a little space, maybe not even a little space, but as long as you understand, okay. But in Mathematica, you have to be precise, because if you did this, you would think it's a third variable. So if this is the case, A dot B will be, guess what? N by n. Okay. Now, before I go a little bit further, let's go back to a dot x. This time, I'm going to say x is coordinate. Okay. So watch this. Watch this. So we did this, right? We list plot. So let's say I'm going to make an assignment again. X is equal to 1 and 1. Okay, it's equal to 1. Now, I'm gonna sidetrack into a concept of what's called algebra. I won't talk about detail. In fact, I'm not clicking this thing right now. But what I want to do is go back to what we did earlier with addition and multiplication. So remember, you recall. Okay, additive identity. Okay, is what? Is 0. Okay, recall 0 is additive identity because you add 0 to anything and it doesn't change, keeps its identity. Okay, you recall that? And this is where, you know, being precise in the beginning of the class pays off. What about 1? 1 is multiplicative identity because you multiply 1 to anything and it doesn't change. So it keeps its identity. Okay. Now, if x is, okay, if x is some number, okay, then let's go back to this thing. I like this original thing. Okay. In other words, let's look at it what it looks like. Looks like this, right? Now, what do you want? What is something that is what is matrix multiplicative? Okay. Now, first of all, it's something that multiply to this and does nothing. Okay. Now, what is this dimension? 3 by 1. 3 by 1. You have to end up with 3 by 1, right? And you remember this? Oops. I keep erasing. I'm sorry, my bad. Yeah, I keep erasing. Huh? Right? Remember this? Okay. Now, if I'm going to multiply A to B, it has to have the same number of column as B has number of row. So definitely, this thing has to be what? Has to be what dimension? Well, it has to be a 3 dimension because you have to end up with 3. 3 by something because you have to end up with 3. And the number of, right? The number of column is also 3 because it has to multiply by this. So this thing is called identity matrix, okay, of dimension 3. Is it true? Okay. Yeah. This is what I want to do, but by the way, I should take it out of the format. Sorry. So identity matrix X is equal to X. Oops. True. Okay, true. My question is, what is identity matrix? It's this. What does it look like? It looks like this. So if basically, if I take this and multiply by this, I should get this. Why? Because when you do this, notice it's nothing. It's just 1 on the diagonal and 0 elsewhere. So when you do this dot product, 1 times this plus nothing else. So you just write it here. Second one, nothing. 1 times this, nothing. You just write it here. So basically, this is identity matrix. It's saying that it's doing nothing. It's doing nothing. Likewise, this thing keeps original dimension. It keeps the same value, it keeps the same dimension. What if I want to keep the same dimension, but different values? So this is where it gets interesting, because I'm going to list plot 1, 1, and matrix A dot 1 and 1. Okay. But first, I have to specify first what A is. So let's say A is equal to identity matrix 2. Okay, so I did this, so it's going to be that, right? So if I did this, what happened? You have 1, 1, and you have applying nothing to it. Now I'm going to change a little bit. Let's say A is equal to, instead of this, A is equal to, now just for fun, I'm going to flip this. Okay. And okay, let's say I'm making something. 1, 2, 3, 4. Originally, I have this number 1, 1. Now I have some funny number 3, 7. Why is that? Well, because what is A 1, 1? It's 3, 7. So if what I want you to see is if X is a 2-dimensional vector of real number, I don't have to, okay, represent 2D coordinate. Okay, then multiply identity, okay, matrix 2 by 2 to it, changes nothing. But if you multiply other 2 by 2 matrix, you effectively move the point. Okay? You move the point. You can move the point. So let's say I have 1 and 1 is not that interesting. So let me do this. Let's say 1 and 2. Okay, 1 and 2. And let's go back to original. So this is, you agree? This is this is nothing, right? So it starts with 1, 2. Start with 1, 2. And it ends up with 1, 2. So it's actually 2 points on top of one another. Okay. Now I'm going to flip that. Now from 1, 2, I have 2, 1. See, this is a flipping matrix. So you can do all kinds of stuff. So you can think of a matrix as transform. So instead now, so you have this. Now go back to think of X as a general representation of object attribute. Okay, so if you multiply 2 by 2 matrix to a 2 by 2 to 2-dimensional vector, you move the point in 2D. If X is a 3-dimensional vector representing 3D coordinate, then multiplying 3 by 3 identity matrix changes nothing, but multiplying other 3 by 3 matrix effectively move the point in 3D. Now, if X is a k-dimensional vector representing object with k known attribute, then multiplying the identity matrix K by K to it changes nothing. But if you multiply by other K by K, you effectively transform. They don't use the word move, they use the word transform, right? So in physical coordinate, you move from one point to the other. In attribute, you transform. Let me give you an example. Let's say you have a girl who is, okay, let me have a girl who is, okay, 52 kilograms with 28-inch waist. Okay, and the matrix, okay, weight loss is equal to okay. So my question is, how has this weight loss matrix transformed this person? She's now 90% as heavy and 90% as circumference. Okay, but this is kind of boring. This is very proportional, right? In real life, you might get something like, okay, it may be something more complicated. Okay, well, this is a little bit too drastic. Okay, so instead of being like proportional, multiplied by 0.9 to everywhere, you transform, you move this person from 50 kilogram, 28-inch into 49.6 kilogram, 24.68 inches. So this is new x, okay, or yeah, so we can say this is all x, this is all u, okay, right? So this is equivalent to something like this, whereas instead of having a two-dimensional location in space, you have weight and weight size, and then you move, but you don't say you move the weight and the weight size, you say you transform the person, you transform the weight, you transform the figure. So this is sort of like before, after, you know, like you see on TikTok or something like that. So this is the old you, this is after this amazing exercise, running, you know, high calorie burn program. After this, the new you is 49.6 kilogram with a 24-inch waist or something like that. Okay, so that's basically what we are doing. We are now, remember I told you that you're going to be working with x, and then y is equal to f of x. Well, this is one form of y. This form of y use multiplication in this way. It will be called linear transformation. And that, in fact, will be the subject of what matrix algebra does. And next class on Monday, we'll actually define all this properly, and we'll come back and do this, but in a proper way. Okay, so I think I went a little bit over time. I kind of forgot to look at the watch. Okay, but so you can see that what we've done today is motivate what exactly you want to do. Okay, this will be called linear algebra. I'll tell you why it's called linear. I'll tell you why it's called algebra. Again, we need a formal explanation of that. But right now, two things we've done today. One is introduce you to the concept of sequence and series, okay, which, although you might not work with in raw form, you will work with it in algorithmic form. Okay. Now, I also introduced the idea of vector and how you can transform vector by multiplying with matrix. Okay, and you know let's say it's the protocol. The protocol is you can do dot product between two things that have the same number of same number of column to the left as something that has the same number of row to the right. Okay, and we'll treat this more formally, and this will be the basis of not only in, you know, obviously in machine learning, we use linear algebra everywhere. You use linear algebra in statistics. You use linear algebra in any kind of data analysis that you know, you can see that, right? If a person is a vector and your data, you have 50,000 clients, then you have a 50,000 by whatever number of attributes table. That's your matrix. That's your matrix. So you're going to need matrix algebra. Okay. And in fact, let me mention that linear algebra or matrix algebra is actually the main mathematics behind quantum computing programming. Okay, but I won't talk about that here. Okay, so I think we can finish with that. I'll see you guys on Monday. Okay, I'll see you guys on Monday. Okay, ครับ